So here we are with some of our examples. And problem one, you probably have seen, I probably put it in some of my earlier notes. This is a Calc 1 question, and it actually has two totally great paths that you can go in. It's sine times the cosine. It's certainly a more complicated integral than just a basic rule, right? If we just remind ourselves, if I fly up here, just close your eyes for a second, there's integral of sine by itself or integral of cosine by itself, but none of our basic rules have sine and cosine being multiplied together. And again, remember that there is no integration rule with a product. There's no product rule for integration. All we have are different methods, and the method, like I said, that we're going to use most of the time in this section is u substitution. Now, it's equally awesome as far as what we're going to employ here, because when you think about it, the power of the sine is odd and positive. We could use, if I fly back, you can kind of look back to page 1, right? If the power of the sine is odd and positive, let's save a sine factor and convert everything to cosines. Well, I also have a cosine factor that's odd and positive. You have two different strategies, and I'm just kind of referring to this flow chart of like they're trying to be helpful here, and I don't mean to make it more complicated at all. You might just have the problem done already, like why is she talking so much about this? There are two paths that you could go in. You could say, all right, let me just try a u substitution, and let me just say, I think what would be nice is to let u equal the sine function. I see where this is going because du, if I kind of work on doing that follow through, is cosine, and this would be my swap for dx. That would be great. You have this integral in front of you. You decided to let the sine x be u. You kind of didn't worry about this cosine that was hanging off on the side there. And then you have that follow through for dx, and that follow through is du over cosine. So this is perfect. Your u substitution totally works. You now have to actually remember to integrate it. You're being left with integrating here the integral of u du, which of course is 1/2 u squared plus c. I will switch this back into our function of x, which is 1/2 sine squared x plus c. Okay. Now that's one way of going about this problem, right? Your other path would have been, well, what if you decided to let u equal cosine? You can kind of see where this is going. You kind of think in your head, the derivative of cosine is negative sine. That's good enough to get me where I want to go, because when I isolate that for dx, I get du over negative sine x. And I come back at that integral right here and say like, well, I kind of ignored that sine function that was kind of hanging out, but I let the cosine function be u this time. And in place of the dx that I had there in that original statement, I'm going to replace it with its equivalent here, which is du over negative sine x. And this is good enough to get you where you're going. You have an extra negative sign in play, but that's okay. You've got yourself an integral where I'll just take that negative and put it outside. And again, we're not going to forget to actually do the antiderivative there. You're integrating u du, so that would be 1/2 u squared. I just have that negative in front. I'm going to convert back to our function of x. These are equally lovely answers. I promise you, they are equivalent to each other. I don't want you to go crazy trying to make your answers work. I'm assuming that WebAssign will count both of these as correct. If you run into a problem, email me. There's that Ask My Instructor feature on WebAssign that a few of you have been using to communicate with me, which is great. But not your job to really worry about it. Let me just kind of take a minute and show you. Not that you have to do it, but for those of you that are curious, like, well, you're telling me they're equal, but I don't see it. They're completely different functions here. Let's once again show how these identities that we talked about on page 2 of our notes together. Let's talk about how this comes together. All right. What this really is, that's cosine squared. I am allowed to rewrite cosine squared as 1 minus sine squared. I'm using one of those Pythagorean identities. Let's walk this through, this problem here, and see where this is going. I can carry that negative 1/2 through. That would change, if I distribute over here, that would change to a positive. And let's just be clear that this is the same thing as what I have over here. What I can do here, this is legal, this isn't cheating or anything, but I can look at, like, I really have the meat of the antiderivative right here. Those are the same, right? And then you just have a constant of integration, which is any number. So these two things sort of combine, and they are equivalent. This really is the same. I can just kind of lump those together. So again, not your job to go from point A here to point B, but I just want to kind of use every opportunity to show you how these trigonometric identities are employed, okay, and how they're used. So I like this one because you have two options, and I like things on tests that have more than one way or more than one legal path forward. Of course, I would grade both of these antiderivative answers as perfectly correct, okay? They are exactly the same, okay? They are equivalent. All right, so let's get into more of our work. You can kind of see problem number 2 down here. This is much more complicated. You start seeing these powers on the trig function. And this is what that first flow chart is sort of mentioning. We can go back to that first page. I can let you do it right now instead of giving you a headache by sliding up and down really quickly. This is one where you have the power of the sign is odd and positive. Okay, the cosine is even. So looking for odd and positive, what I'm going to do is try to save a sign factor and convert everything over to cosine. So let's actually do that. I'm going to go step by step here. This is sine cubed. I'm going to write it. They said to save a sign factor. Fine, let's pull that out. But I also then have sine squared hanging out, right? Because sine times sine squared is sine cubed. I didn't even touch the cosine yet. I just kind of left that off. And their advice here, which is really what that flow chart is, it's their best advice to give you, convert the remaining sine factors to cosines. That means I'm zeroing in right here. We're going to save this. This has to stay. And this has to get kicked out and rewritten in terms of cosine. So here's that Pythagorean theorem again. I am going to swap out sine squared with its legal representation, which is 1 minus cosine squared. I am making that swap right there. It's legal, I can do it. Remember, I'm saving that first, single sine factor. This, I want to make sure that I hold on to that. I'm saving that intentionally, okay? So what I'm going to do, this is all equivalent. All I've done is change the integrand a little bit. And I'm going to use that really good idea. What I'm going to use here is I am going to do a u substitution, and I'm going to do it so that I let u equal cosine. Anytime I decide to do a basic u substitution, of course you have that follow through, and I'm going to rewrite it in terms of dx. Okay. So I'm going to work on this, and I'm going to do this. And let's think about what we have with this integral. Remember, this sine function is staying put. I am not messing with that. But anywhere I have a cosine, I can replace it with u. So let's be clear about what's happening. What I have is I have 1 minus, and now I have cosine squared. So I'm going to say u squared. And then over here I have cosine to the 4th, so remember, u is cosine, so that's going to be u to the 4th. Okay. Now, in place of that dx over here on the side, remember what I'm doing, I'm replacing it with du over negative sine. And that's the whole reason that you saved this sine x here off to the side in the beginning, right? It's still inside your integrand, but you were hoping that this is going to go away, and it does. It totally vanishes. I've got this sign that you were saving to totally cancel out that sign from that dx follow through. I'm just going to circle that negative sign so that I don't forget about it. And then I'm going to kind of work this through. What I really have created here for myself is I've got a negative on the outside, and I have this integral, 1 minus u squared u to the 4th du. So you have really transformed this integral that was, you know, crazy trig functions into something polynomial looking. That's the whole point of u substitution, is that it starts to look friendly. And we know how to do this because what I'm going to do is just move that u to the 4th through. I'm just going to, let's see. I'm just going to throw that in and multiply it through. So that's u to the 4th minus u to the 6th. Now I can get in here with the power rule and work this through. So what do I have? Well, I'm going to have 1/5 u to the 5th, 1/7 u to the 7th, and then maybe I'll throw the negative through. Now notice I didn't box that answer because, you know, I mean, my integral had trig functions in it, functions of x, and this doesn't. Well, let's go back. Remember, we let u equal cosine, so let's rewrite it. My answer here would be negative 1/5 cosine to the 5th x. You can write it like that, or you could just kind of go like this, 1/7 cosine x in parentheses to the 7th. Both are amazingly great, but that is my final antiderivative. Okay. So that's how this flow chart kind of works. They're telling you to save something intentionally so that your u substitution works out perfectly and you don't have to try something a second time or a third time. You don't have to reimagine that wheel. Okay, so let's come up with example 3. And it gets a little bit more interesting. Again, there's nothing basic about this integral, right? This is not a basic structure. But notice how this has, the power of cosine is odd and positive. And so if you think about that flow chart, they say, hey, why don't you save a cosine factor? And then we're going to convert everything over to sine. So how is that going to work? Well, I'm going to do the same thing. I'm going to save one cosine factor, which means I have, you know, the cosine there by itself, and then cosine squared, that combines to give you that cosine cubed. And then I'm just kind of ignoring this square root of sine x in there, like it's just kind of there. I'm going to convert everything over to sines. That's what they want you to do. So that means I'm going to really kind of look at this cosine squared here, and I'm going to legally swap that out with a trig identity. Again, the Pythagorean identity. Cosine squared is the same thing as 1 minus sine squared. So I'm just making that swap. It's legal. I'm going to keep everything else there, right? They told me to save that one cosine, so I'm doing that. And now I'm going to, you know, go through my u substitution in this case. I'm going to say, well, what am I doing? I'm going to let u equal sine. And anytime you're doing a u substitution, of course, there's a follow through that you've got to identify. And for the purposes of what I have here, I'm going to solve this for dx by itself. So now I'm going to come at this integral and say, okay, well, I had this cosine. They told me to save it off to the side. I did that. What else I have in here is I've got anything with a sine. I'm going to replace that with u. So let me undo that. I have 1 minus, and now I'm going to have u squared. And then I have the square root of sine. So what is that? Well, that's the square root of u. And in place of the dx, remember, I'm replacing it with du over cosine x. And the reason that I kind of left this cosine off here off to the side is because I wanted it to go away. That cosine cancels with the follow through, so this is a perfect execution of u substitution. They gave you exactly what to do to make this work on the first shot, because u substitution doesn't always work out like that. So what do I have left over? Well, I've got this integral that's really 1 minus u squared, and I'm going to write the square root of u as u to the 1/2. I'm going to employ the same strategy that we did in the last example of like, okay, I don't have a product rule for integrals, but I can easily kind of distribute that u to the 1/2 through here. And so let's see, when you're multiplying here, you're adding the exponents. So 2 plus 1/2 would be 5/2. Now that is not your power rule for integration here. I'm just working out the algebra. Right now, I'm actually going to use the power rule. I'm gonna say, well, if I'm integrating u to the 1/2, I'm gonna add 1 to the exponent and divide by our new exponent. Dividing by 3/2 is the same thing as multiplying by 2/3. I'm going to add 1 to the exponent, so that would be 7/2. Dividing by 7/2 is the same thing as multiplying by 2/7. That's your antiderivative, which you're certainly not done because you have not switched back to the function of x. I'm going to remind myself that I let u is actually the sign, so I'm going to come in here and just rewrite that final statement. 2/3 sine of x to the 3/2 minus 2/7 sine of x to the 7/2 plus c. There is your antiderivative. Okay. And now we come to the last one that I'm going to do in this video, which is that idea of like, well, I definitely have something complicated. I have that sine squared of 3x. This is what your flow chart kind of tells you, like, okay, if you have sine squared or you have just cosine squared, you can reduce the power there. A Pythagorean identity would not work because you can only replace sine squared with a cosine squared. So you'd sort of be in the same problem. But the power reducing is the way to go. So that's what we're going to use. We're using what they call that power reducing identity. Okay, so this is legal to do. And so let me start it out. Right? In place of sine squared 3x, what am I going to replace it with? Well, I'm going to look at it and replace it with 1 minus cosine of twice that angle. So twice 3x is 6x. And then you put it over 2. Now I have a tendency of, I don't really want to see this as a quotient because I feel like it looks more complicated. Let's just like break this apart from its common denominator. Let's say it's 1 over 2 minus 1/2 cosine 6x. I'm just kind of breaking that thing apart. And so, you know, when you're thinking about an antiderivative, I mean, they're separated by a minus sign. This is why we did this. This is much easier. I can integrate 1/2 dx really quickly. That's just 1/2 x. I'm done. That's my antiderivative. Now what I have to do over here is I do have to deal with this integral that I didn't address yet. 1/2 cosine 6x. You can definitely take the 1/2 and move it outside the integral. I think I'll do that. That's fine. But this right here is an integral that you definitely talked about in Calc 1. This is your sort of basic idea of what a u substitution can be used for, something composite, right? You got the 6x sitting inside the cosine. This is the perfect opportunity. I can get this done just with my old familiar skills from Calc 1. Let's let that be u, the 6x. Let's go through the whole follow through. And let's put these puzzle pieces back together. I still have that negative 1/2 flying around, but I decided to let the 6x be u, and I've got this follow through here of du over 6 for dx. So things are looking good, right? Because I can take that 6 and move it out, and that just basically turns that coefficient on the outside to a negative 1/12. I know the integral of cosine u du. I know that that is sine u. Now, I don't want to forget about this 1/2 x that was kind of hanging out that I was ignoring for a while. That is part of your answer. Let's slide up so you can see it. So this kind of looks awkward, right? Because you have 1/2 x minus 1/12 sine u. You have to switch this over. This is not good. Let me see if I have enough space here. I'm going to say, well, let me get this all in terms of the x variable. And that's what I'm looking for your final answer here. Okay, so we've kind of handled everything in that first box of your flowchart. What should you let u equal, and why does it work, and how are we using these identities to sort of reimagine these integrals and get us to move forward?